about automatic SQL error mitigation in the Oracle database. So as we all know, bugs in software are a reality, and that's more so in a complex code base like the Oracle database. And when these errors happen, they disrupt the application workflow and lead to a bad user experience. And they can be more disruptive in cloud deployments because often there is no human administrator in this situation. So we wanted to design a solution for this problem. So our proposal is called automatic error mitigation, or AEM. So what does AEM do, right? It automatically mitigates errors that arise during query compilation. And the process is fully transparent to the users because AEM intercepts the error internally and mitigates it, and the user isn't aware of it at all. And this framework is also extensible to other modules in the database. So let's take a look at the AEM architecture and control flow here. So looking at the picture on the right side, the user query is being submitted from here. So let's assume the user, and when it hits an error, AEM catches that particular error, and the first step it does is it uses the optimizer context information that's available at that time to generate what we call fine grained hints that help correct that particular error. After that point, it tries to reproduce, it actually looks for alternate plans that are available for that SQL statement. Alternate plans are historical SQL plans that are available for statements. So it looks for those plans and it tries to use one of them. If it succeeds in finding a plan and it succeeds in reproducing it, it can switch to that plan. Otherwise, it proceeds to use the fine-grained strategic hints that it generated earlier to mitigate the problem. If it succeeds in mitigating the problem, then well and good, right? Otherwise, it proceeds to use global strategies, what we call global strategies. And currently, it uses optimizer version hints to actually switch the behavior of the optimizer to an older version and to check if the problem goes away. If any of these strategies succeed in avoiding the error, it creates an object for the SQL statement called SQL patch. This SQL patch contains that error correcting hint. And at the end of it, it recompiles the query, and the recompilation would pick up the patch and help avoid the problem. And if none of this works, of course, the error is raised to the user. Now, I'm not going to talk about how AEM switches to alternate plans, but instead focus on how AEM generates and uses SQL patches to fix these errors, or to avoid the errors. Sorry. So before we delve into the details of fine-grained hint generation, let's get some terminology out of the way. So there are two things that we need to be aware of. First thing is the query rewrite techniques in Oracle are called transformations. So these form part of logical optimization. And the second thing is hints in Oracle target query blocks using query block names. So they do not apply to the entire statement, but they can target individual query blocks. And query block names themselves are deterministic hash signatures that are generated based on the operations that are applied on the query block. So as an example, let's take a look at this query Q1 on the right side. It has two query blocks, $1 and 2, and there are two transformations that are applied on this query. The first is view merging that names the query block to the one that ends in 74E1. And then another transformation is applied on this query block, which is called place group by, and it renames it further to the name that ends in EA2A. Okay. So at this juncture, let's consider that an error happens when the optimizer is applying transformation GBP, that's place group by placement transformation. So by this time, as it already applied the view merging transformation on the query blocks, we have a query form that is Q1M as shown in this picture. It has 3 tables. And it's about to apply group by placement at this point. So when error happens, the transformation context contains 2 parts to it, right? So the first part is the query block name itself that was already generated. And the second part is what we call the state of the transformation. That is the state of GBP here. Now what is the state? right? So each state of a transformation corresponds to a rewritten form of the query, and that is specific to the transformation. In this particular case it is GBP. So each state of GBP corresponds to a rewritten form that combines the tables in certain ways to create these groups. So what GBP transformation essentially is doing is it's grouping the tables before they're joined with each other so that the join becomes more efficient. So as we can see here, there are I show three states in this particular picture: 110, 101, and 100. That and corresponding to each of these states, there is a different combination of tables that are placed in each of these groups. So, for example, for state 101, the query Q1T shown here at the bottom is the rewritten form of query Q1M that we saw earlier. So, this creates two groups and places different tables in them and then joins the groups together. Now, let's assume that an error occurs when the optimizer is exploring state 100 of this transformation. So, in this particular state, AEM has two options to generate fine-grained hints. The first hint is a no place group by hint that uses the query block name, and it also uses the state S and D1, D2 in this fashion. That comes from the 100 state here in yellow. So, and this particular hint disables that specific state of the GBP transformation. So, the other hint that gets generated is a no place group by with just the query block name. And this hint disables all states of GBP instead of just one state. Now, there is a third option where the AEM framework can generate a hint that disables a subset of states instead of one state, particular state, or all states, right? That's used by certain transformations as well. So why generate these fine-grained hints, right? So the benefit of these fine-grained hints is that they're less disruptive to query plans. Now, why is that so? So they're less disruptive predominantly because of two reasons. So the first reason is because they are targeted towards the erring query blocks and the states. So they do not apply to the entire statement, but they only apply to a particular query block. And the second reason is that they're conditional. So because they're using query block names, and by conditional, what we mean is if a different query block name is generated in a separate compilation sequence because a different set of transformations are applied there, the hint is basically a no-op. The hint is ineffective. And that's desirable because often errors are related to a sequence of transformations that are applied on the query block. And it's possible that an error doesn't occur when a different sequence happens. And so we don't want these hints to interfere in such a scenario. And continuing on those lines, if we look at what is the impact of these hints on the final plan, if we do a qualitative assessment, so essentially there are two possibilities where these errors can happen. Right? So the first is that an error can occur in a non-best state of a transformation, in which case the optimizer would disable that non-best state as an error correcting strategy. But there is no impact on the final plan because the optimizer wasn't going to choose that state anyway in the plan, right? But if on the other hand the error occurs in the best state of a transformation, in that situation there is a change in the plan because now optimizer switches to the second best state, and subsequent transformations that are applied they work on this second best state. So potentially there is a different plan at the end of this sequence. So this is the only situation where the plan can change. And another point to mention is that there are n-1 non-best states in a transformation, whereas there is only a single best state of a transformation. So the vast majority of cases fall in the prior category. So let's see an example. Okay. So in order to illustrate the benefit of fine-grained hints, we took a look at TPC-DS query 4 with the scale factor of 1 GB. That's a small scale factor, and continued to look at GBP transformation that we discussed so far. Right? So query Q4 has two query blocks of a union all set, and GBP is applicable to both the query blocks. So if we look at the default plan that the optimizer comes up with, this is a no error plan. Let's assume there is no error in this plan. Now we can see that in the plan, cell $1 and cell $2 shown in blue here are the two query blocks where GBP is applied, and group by placement has taken place in both these query blocks as it created these groups. Now consider that we disable the best state of GBP on cell $1 because an error happened. Now the optimizer switches to a second best state in this situation, and we can see here that the groups have been created in a different, slightly different fashion. And the cost of this plan is 1875K. The cost of the original no error plan was 1872K, so the cost has gone up slightly. Cell $2 meanwhile in both these plans is the same because there is no impact on this query block. Now if instead we disable all states on cell $1, all states of GBP by generating the appropriate hint, right. So in that situation we see that now there is no GBP in this query block at all, cell $1. It does regular joins of these tables, whereas cell $2 continues to remain unaffected, but the cost has gone up to 8178K in this case. So it has become more expensive. And then finally, if we use an older optimizer version to generate the plan, so we can see here that query blocks cell $1 and cell $2 both have no GBP in them, and the cost now is 32M. So this is an example to illustrate the benefit of fine grained hints and how they can be less disruptive to the query plans that get generated. And let's also look at some real world data at this point, right. So we actually went and surveyed a set of compile time bugs that have been reported on the Oracle database on cloud over a period of 1 year, and we further trimmed down that list to the bugs that qualify for AEM and also that are reproducible in house. So that gives us a total of about 104 bugs here. So if you look at the chart on the left side that shows the division, 36 bugs that are on the left here have no workaround, meaning AEM cannot mitigate those bugs. 26 bugs could be mitigated by a foreground strategy by generating fine grain hint strategy by generating these fine grain hints, or an optimizer version hint as well. 36 bugs here could be mitigated only by using an optimizer version, and 6 bugs could be mitigated only by fine grain hints. So that gives us, if we add up all these bugs, that gives us about a 65% success ratio where AEM was able to mitigate these errors by using one of the strategies. And that's a good result for us. That's actually very effective result for us, because if we are able to mitigate about 65% of errors in the real world case, that's a big win. And we also delved a bit deeper into what optimizer versions are successful in mitigating these errors. So that is the information that's shown in the chart on the right side, where we see that the older optimizer version we use, the more number of bugs that we are able to mitigate. And finally, I want to mention a few future enhancements that we have planned for AEM. Right. So currently AEM uses a first fit model. What that means is it stops at the first success. When it finds a mitigation strategy that works, it stops immediately and uses that. But instead, we can also look at extending this to consider what we call a best fit model, where if there are multiple workarounds that all succeed in avoiding the error, we want to be able to use the best one among them. Right? So we can use the optimizer cost as a proxy to find out the effectiveness of a particular workaround. So this is essentially a trade-off between the time spent in mitigating the error and the quality of the plan that ensues out of that effort. And the second extension that we plan for AEM is to mitigate SQL execution errors as well. So this is a bit more challenging because we have to deal with partial results and query restarts and parallel query execution, etc.